So, in the last class we spoke about our projected gradient algorithm, we spoke about the optimality condition when a convex function is not differentiable, and our optimality condition was something like this, that so if you are trying to minimize a function, say a convex function phi over C, a convex set C, then we said that if x bar is a local minima, the necessary condition is global minima because it is convex. So, we are writing down the necessary condition. So, x bar is a global mean, then for each x in C there exists xi x belonging to, depending on the x you choose, the subdifferential of phi at x bar, such that xi of x minus x bar is greater than equal to 0. Means for all x pi I wanted to say that whenever you take an x, your xi x would change. This condition is also sufficient. So, as a homework, show that if I write down this as the condition star, the condition star agreed. Now, this does not look very interesting because at every x you need to change, but then how do you go ahead and prove something better? How do you improve this condition? By improvement, what we want to tell is that I want to get one xi which will work for whatever x you take, only one xi which will work for whatever x you want to choose, right. Okay. How do I get such an optimality condition? Let us first start with this thing, try to give you an answer, and then try to pass on to our study of penalty methods, where we are supposed to study today an approach which will be specifically done for equality and inequality constraints. We will tell you how to write down the penalty function and show what would happen if you take a sequence of local minima of the penalty problem. These are all helpful when you actually study algorithms, because you really know what the thing is going on, suppose if you apply penalty methods. So, let us look into this problem for a while. You can look into my course in NPTEL, it is on convex optimization, you would get more detail on this, but we are not going to go into so much detail, but okay, try to tell you a bit more. So, how do I go about this? So, what we intend to show here is the following, that x bar is a global minimum if and only if there exists x bar is a global minima if and only if there exists xi element of such that so this xi no longer depends on this x. So, this actually means it is equivalent to the following condition. Which is equivalent to the condition so this is set addition, that is which here we are adding two sets. I want to recollect that adding two sets A and B in Rn means it is a collection of all z, where z can be expressed as x plus y with x belonging to A and y belonging to B. So, you take any arbitrary element of x and A and any arbitrary element of B and make a vector addition of them, and the new vector that is formed, that is in the set A plus B. So, this is what ultimately we need to prove. In order to prove such a thing, we need to get into a slightly different fact. The different fact is that for a convex function, suppose you calculate this particular limit, fix up the h, a vector, and then you calculate the limit at any x over whole of Rn. Now, this symbol actually means lambda is strictly bigger than 0 and lambda goes to 0. So, this is called lambda down arrow 0. Now, this is, if this limit at all exists, then this is called the directional derivative of the function phi at the point x and in the direction h, phi dash of x comma h. Now, for a convex function phi from Rn to R, so if phi is from Rn to R, this always exists. But this basically means this for always exists in all directions. So, at a given point h in x in Rn, whatever direction you choose and you try to compute the directional derivative, the directional derivative would exist even if the original function does not have a derivative. For example, if you take this one, if x is absolute value of x and you now try to compute the directional derivative at h at 0, because 0 is the point where you do not have the derivative. So, it is 0 plus lambda h minus mod of 0, because phi of x is phi of 0 is 0 divided by lambda. So, basically it finally means lambda by mod h, the lambda is positive, by lambda which is mod h limit. So, finally, because lambda cancels, because lambda goes to 0, lambda need not be 0. So, it cancels. So, as lambda goes to 0, so this is nothing but mod h, because mod h is independent of lambda. Now, so this is a function of h, and this look is a very interesting thing. It looks like that this is the same, it has the same function structure. Now, so this once I fix the x, if I fix x, once I fix the x, this is a function of h. So, this is a very important point to remember. As a function of h, phi is positively homogeneous, that is phi dash, and also phi dash x of H1 plus H2, it is subadditive, it is positively homogeneous and also subadditive. So, these two properties, this is subadditivity and the other is positive homogeneity. If a function has these two properties, then this function is called sublinear. So, this is obviously it is a convex function, you can show that this is obviously a phi dash is a convex function in H. So, it is very important to know that this is a convex function in H. And if you have the derivative, so if phi is actually differentiable, then you have, this is exactly the value of the directional derivative at H. And here you see, if it works for lambda negative, that is lambda comes from the negative side and goes to 0, then if the limit exists and is equal, then of course the derivative is there. So, we have some few examples. So, what is its relation with the subdifferential? So, relation with the subdifferential is the following. It is very simple to show, which I am not going into detail at the present moment, and you need to go to my convex optimization course, or maybe in future I should give a course on convex analysis proving all these things in detail. And so, here it is not very difficult to prove, which I will keep as homework. So, whatever xi you take at the whatever xi you take from the subdifferential of phi at x of the convex function, this result always holds. In fact, it can be shown that this is a very important fact, and it is truly a very fundamental fact in the sense that it shows the power of separation theorems, but we have not dealt with separation theorems here in so much rigorous way. So, we are just going to give you some very basic idea. What happens is that you can always write so, once I fix my h and x, this becomes a function in xi, a linear function in xi, and you are maximizing it over a convex compact set. And in fact, because of the compactness and the continuity of the linear function, there exists a xi for every h, there exists a xi for which this will be true. Now, this duality, that is this going back and forth between the directional derivative and the subdifferential, is a key thing in convex analysis, which is a key tool in understanding modern convex optimization or modern optimization as such. So, here we tend to first look into we will try to look into a very fundamental optimality condition which relates, which makes use of this in the constrained sense, in this sense of minimizing it over C. We will not talk about minimizing over Rn, because minimizing over Rn is not a very difficult thing. X is a minimizer of phi over Rn if and only if phi dash xh is greater than or equal to 0 for every such direction h. Okay. Now, once I try to look into the set C, the geometry of the set C would play a significant role in understanding what should be the necessary condition for optimality. So, let us have a convex set C and let me see, maybe this is the point which is optimal. So, what do you expect at this point? Why would you call it optimal? Because if you move from x bar along any line till you and the points till you stay in the feasible set C, at every point the function value would always tend to be more than, it should be more than f of x bar. So, function value at this point should be more than the function value at x bar. So, if I move along any such points, any such direction, basically my directional derivative should be always greater than equal to 0. Basically, if I have, for say if I take lambda between 0, a very small number much less than half, say 1, and we are pushing it to 0, and suppose for lambda sufficiently small, phi of x plus lambda h for a given direction h is in the set, this set C, for all such lambdas, then it is immediate that for such directions h, this would be greater than equal to 0, or phi dash x h would be greater than equal to 0 for such directions h, for which this is true, that x plus lambda h is in C. So, for every such direction, for example, if I take this direction, obviously it is not true because it is so much outside the set from the very beginning. So, ultimately if you look at all such directions, you would finally come to a set of directions like this on which this condition would be true. This set of directions here form a cone, and that is called the tangent cone to the set C at x bar. So, this takes us slightly into what we would call non-smooth geometry, and we would write down a bit of definition about the tangent cone. Let us again start looking at this cone and see how we can mathematically describe this cone. What is happening here is that if you look at this, we are basically looking at, say, if you look at a sequence of points coming along this boundary towards x bar, and then you keep on drawing the rays or joining them by the join x bar by the line segment. If you keep on doing so, you see ultimately it comes and converges to the tangent line, the very simple notion of a tangent line which you already know from your high school. So, basically if you look at sequences, so if you take sequences, you say why sequences, why not a curve or why not a straight line. The question is that here this definition can be extended even to non-convex sets which could be even disconnected, and in the sense that their sequence would be much more easy to describe things. So, if you take any sort of sequence of xk's in C coming and converging to x bar, and then you take those line segments and scale them up, and then see the direction to which they are converging, then that sort of direction is usually called a tangent direction, motivated by the fact of the definition of the tangent. Because you are using the same procedure as you would like to draw the tangent to a curve at a given point, the same procedure is done to generate the whole cone. So, this cone is usually known as the tangent cone or the Bouligan tangent cone. It will be just for us, let us just call it the tangent cone rather than getting too much bothered with historical correctness. We should call it Bouligan tangent cone. It came around 1938. So, what it says is the following, that so what you do, you consider a sequence xk with each xk element of C and have such a sequence which is converging to x bar. Now, scale it by some number, so that it just does not become the 0 vector. you stop it from becoming 0 vector, so that you really observe in which direction there is converging. So, divided by some Tk, where Tk goes down to 0. So, here as Tk is going down to 0, the scale factor is increasing and stopping this norm of xk minus x bar to come down to 0. So, this goes to certain vector v, and this vector v is called the tangent vector to C at x bar. So, v is called the tangent vector Now, once this is known, you can now the set of all such vectors v is brought up in a cone, and this is called the tangent cone to C at x bar. So, v is called the tangent vector to C at x bar if there exists an xk going to x bar such that and a sequence tk going to 0 such that this ratio, the limit of this ratio goes to that vector v. So, that is the meaning of the tangent cone. Now, what does the tangent cone tell me? Can it give me some information regarding the information it gives is the following information. Now, what does it tell you? Okay. So, it tells you that I can write, if I write this as Vk, then I have xk equal to x bar plus tk Vk, and this is an element of C. Okay. You can write it like that also. Now, since C is a convex set, so I can write x bar plus some lambda times, lambda is between 0 and 1, this vector x bar plus tk Vk minus x bar, this is also in C. So, once you know this, then that will give you x bar plus lambda tk Vk is element of C, right. So, for all lambda between 0 and 1, this would happen. This is the outcome of convexity. Okay. Now, if x bar is an optimal point, then you write, you take the direction tk vk for a fixed k, and then because you know that, so whatever k you take, this means that for any k you take, this is always in C. So, this minus phi x bar must be greater than or equal to 0. Now, if I divide this by lambda, and take the limit as lambda tends to 0, down arrow 0, this will give me that phi. So, I fix that k for a fixed k is fixed. Phi of x bar Tk Vk is bigger than equal to 0. Now, the next step is very simple. So, because my k is fixed. Now, what I will do, once I know this and I know that there is a positive homogeneity of this directional derivative. So, this is the directional derivative. So, the positive homogeneity of the directional derivative would tell me that I can take the Tk out, and as Tk is strictly bigger than 0, I can divide by Tk. So, I can write Tk times phi dash x bar. Of course, Vk I am taking as non-zero. Okay, 0 is in the tangent cone. I do not want to bother about 0 vector. 0 is obvious, because if you put h equal to 0 here, this will become 0 by definition. So, this is greater than equal to 0, and phi dash x bar Vk is greater than equal to 0. Now, because for a fixed x bar, this is a convex function in H over the whole of Rn, which means that over the whole of Rn, this is a continuous function, because every convex function is continuous over the whole space. So, I can now take as limit as k tends to infinity, I can push the limit in here just by basic definition of continuity. That would imply that phi dash x bar v, because Vk goes to v, right, this Vk obviously goes to v by the very definition of a tangent cone, this is greater than equal to 0, but this v was just one of the members of the tangent cone. So, if I take any other member, I can repeat the same argument to give me the following fundamental necessary and sufficient optimality condition. This is necessary as well as sufficient. So, why it is sufficient is still a little bit of story, which I will not tell you right now, maybe you need not even bother about it. This is what you have. The tangent cone has some sort of a strange relationship with the normal cone, not strange, I would say rather nice geometrically. So, the tangent cone, the normal cone to C at x bar can be written as set of all v such that v of w is less than equal to 0 for all w belonging to the tangent cone to C at x bar. Symbolically, this means this is called the polar, this set is called the polar of the tangent cone, given by this notation. Now, what is important here is to know that how that is true. Can I take an element of the normal cone and write it like that? Because if C is a convex set, then the tangent cone has a more simplifying, because of the convexity of C, the tangent cone has a more simplifying expression. What you essentially have to do is to take the cone generated by C minus x bar and then take the closure of that. That is exactly the tangent cone. So, see this set C minus x bar and the cone generated by this is nothing but a set of all y, where y is written as beta times z minus x bar, z is element of C and beta is greater than equal to 0. So, you take C minus x bar, basically now basically you have translated the cone to cone's vertex at 0, basically this is now x bar is now put at the origin, and then you are drawing a cone, you are generating a cone. So, you know how you generate a cone, if you just recall I guess. So, if you have any set C, so you can just, this is the way you generate a cone. Of course, if you take a convex set C, it will always generate a cone which itself is convex. For example, this is a, but non-convex sets can also generate convex cone, they can also generate non-convex cone. So, this is the cone. So, the cone generated by a set C is a set of all y, where y is lambda times x, where x is in C and lambda is greater than equal to 0. So, this is the standard definition which we usually learn in the very basics. So, I am packing in a lot of convex analysis in this lecture. Now, once you know this, so take any V, take V element of NC x bar. So, once you take the V element of NC x bar, your immediate formula that you know is this. X element of C. Now, once you know this, what would happen is the following. Now, I can multiply it by beta. So, I can do that for any given x, and then I of course can take the limit of such quantities. So, you will simply have V of W. So, any element here would lie down here. How do you know that any element here would be actually there? It is obvious, because x minus x bar, if x is in C, x minus x bar is naturally element of TC x bar, and hence this would be true. So, any element here is automatically here, and by this, again by this simple procedure, any element here is automatically here. So, you know this fact. So, then keeping in this fact in mind and using the separation theorem, from there you can conclude the following fact, that 0 belongs to So, this is a very important fact, and knowing some of these facts are important, because we are going to study duality in after one class I guess. So, now we will go back to what we were trying to study about penalty functions. So, we will now write down a standard equality inequality constant problem, and we will try to see how do you construct the function Px, right, the penalty function. From this part of the board, I am sure that you have observed, but anyway there is a video, you can go back and check. So, what is very important here is to note the following, is that is the following, that okay, let me consider this problem. Now, for this problem, how do I construct the penalty function Px? is usually called the Beltrami penalty function. See, this penalty function is usually given like this. So, you basically take the max of between Gix or 0 and take the whole square, and you do it individually for all the i's and sum them up. The interesting part here is that if you do not take the square, then max of Gix 0 is not a differentiable function. It is a non-differentiable function in general, but if you put the square, it becomes a differentiable function. It is very important at the outset to know that why such a problem is, how to compute the derivative of at least this one, because you see we will basically consider ourselves studying this function. Where Px in this case would be this. Okay, when we would actually write some results about this, we can just forget this part, just concentrate on the inequality constraint for the time being, and the other part can go as homework. Now, the interesting part is how do I compute the derivative of this? I have not seen any book which actually does a little bit of, gives a space to do it, because everybody might not be so comfortable in computing the derivative of this. Let us see first how do we compute the derivative of this and finish our today's journey here and continue from tomorrow about the property of this class of penalty function. What does it give me? What does it tell me if I solve and get a local minimum of each of these, and where does the accumulation point of such a local minimum lie, or what is its property? Because here is a practical issue. So, in practice, are we really seeking an optimal point, or we are happy with some point which satisfies the Karush-Huntakar conditions? So, I am supposed to find the derivative. So, I will take a function like this, phi x is max of say a single function Gx 0, and I am taking a whole square of that. So, what would I do? So, here observe certain simple facts. Simple facts are like this, that I can compute the gradient of this, but how do I do it? So, basically I start computing the directional derivative, and if I can express the directional derivative as some function v into h, then v basically I can take it for lambda in any direction, then I and get the same answer, then I have the derivative, that is for lambda minus 1 and plus 1, okay. And lambda in the direction of minus 1, lambda in the direction of plus 1. So, now let me look at it. So, if I look at the directional derivative of this problem, basically then I am trying to compute the limit say at x bar I have to first compute this fact. Now, you see here my Gx bar could be 0, Gx bar could be positive, and for the moment I assume now this could be 0 and this could be. The problem is that if this is positive, this has to be positive. If this is 0, it could be 0 or positive, it does not matter. If this is positive, then this has to be positive because of the continuity of the function phi. So, this function overall is a continuous function. Because of the continuity, for lambda sufficiently small, whatever direction h you choose, phi x bar lambda h is positive by the continuity of the function. So, suppose now phi x bar is positive. If it is 0, then we can of course a similar thing can be done. Then what I can do is so what I have now is g of x bar plus lambda h whole square minus g x bar whole square, and that divided by lambda. But now here I open, because I know that g is differentiable. So, g is given to be differentiable. Of course, here we are only studying differentiable problems. Please note that we were studying only differentiable problems, these are all differentiable. So, then what would happen is the following. Then I write down by the definition of derivative if you look at this a plus b plus c whole square, that then you will get basically a square plus b square plus c square plus 2 into AB I just pulled in the Gx bar into this AB, AC, BC. Okay. 2 of course plus this into this. So, now I subtract Gx bar from this thing, and the whole thing actually is now divided by lambda. Now, you see this thing cancels, and now what I have here first is, from if I divide by lambda, I have lambda so I have this. O lambda square I can write, I can multiply top and bottom by lambda, and I have lambda, O lambda, O lambda. If I multiply top and bottom by lambda, it will become lambda square in the bottom. So, it will become lambda, lambda plus, now if I divide it will become 2 Gx bar okay. Here will become 2 Gx bar O lambda by lambda plus lambda times grad Gx bar H O lambda by lambda. Now, you know small when we define the derivative, we have given you in the definition this, you know, the small o quantity O lambda by lambda, that is actually going to 0. Now, when lambda goes to 0, this will go to 0, this will obviously go to 0 because this is going to 0, this is going to 0, this is going to 0. Now, here it is free of lambda, so this will remain, but this will go to 0 and this will go to 0 and lambda, this part is going to 0, this part is going to 0. So, which means now what is left over as lambda goes to, so as lambda goes to 0 plus, in fact 0 plus 0 minus does not matter, whatever, basically as lambda goes to 0. What I am getting here is 2 times g x bar grad g x bar h. Now, if g x bar was strictly less than 0, then or equal to 0, this would become 0. So, this is my derivative actually. So, but basically then this is either g x bar or 0. So, I can now write the gradient of phi at x bar is either it is 0 because this becomes 0 or it is this. So, basically it is max of twice into max of g x bar 0, this whole thing into grad of g x bar. This is my actually the required derivative of this. So, this calculation is quite important, you can try it out on your own, and once you learn some non-smooth calculus, for those who are really deeply interested in optimization, they will learn. So, then for them it will be simpler because that will be just an application of a non-smooth calculus rule. So, with this I end my talk here, and tomorrow we will start to see the nature of this thing, and we will talk about something called exact penalization, and then go over to study the use of Lagrangian duality and maybe a sort of idea of how to use Newton's method in the constraint case. Thank you very much.